be attentive in spite of it. We're going to be talking about the CPU roadmap and some things we've been working on to bring some improvements there. But first, just a quick recap to help frame our thinking and the goals of CPU as they harmonize with the XLA goals, which is, we want to unlock access and exploit that hardware regardless of framework. That's core to how we're held together, and that continues on with what we're doing with the CPU side. And we want to have the ability for you to get industry-leading performance out of the box with as least friction as possible. And we want to pave the way for people that can help us do that. And we want this platform to be one that endures and is durable and is community-centric, because we know that we're only as good as our users and customers and our participants that help us build it. And of course, this is a crazy rapid field. We were just talking over lunch about what life was 6 months ago. So velocity and being able to work with that is key. So that's how we look at XLA. And then if we drill down into what that means kind of for the CPU, on one hand, despite our aspirations to move quickly and have more and more capabilities, we do have a number of customers inside and outside Google that already rely on the CPU compiler. So the idea we would torpedo and start over was really not in the cards. We were thinking about how can we exploit the goodness we have in the ideal way that can help us evolve what we're doing to be more effective, and yet provide that continuity for people that are already using it. We want to have, the GPU is kind of where all the excitement is right now, but in the sense that we think that we want to continue to provide excellence in the CPU side, and be ready as that story evolves through who knows what happens next in the hardware space. And we want this to be an entry point that's effective for our partners and users, to be easily extendable. We've gotten some feedback that sometimes extending XLA is a little bit like OpenXLA is somewhat like a experimental process where you have to kind of do work to figure out where to connect. And we wanted to make this something that's not a trial and error or explorative kind of thing. And again, we talked about the cross-framework support, and meanwhile also exploiting libraries. So with that framing, I'm just going to hop into a diagram, and then I'm going to have a few slides on the specifics. But like I mentioned, we aspire for framework agnosticism on it. And as you'll see, we absorb and intake TensorFlow, PyTorch, and JAX by way of a stable HLO, as we've all known worked with before. And then we ingest stable HLO into this large, as people have been on this project, been calling the purple box. That's the set of passes and the capabilities that are in the OpenXLA compiler today. And in a sense, you could think of, there's three extremes we could have taken when we considered how we could have worked with these passes, of which there are around 40 some in the CPU compiler today. We could say that all the work happens pre-passes and that the compiler really doesn't provide you work for library integration at all. Or we could say the library integration would happen after all the passes. But that isn't ideal because we mutate the graph to an extent and do bufferization, which is too hard to undo. And that's not a good result either. There's some medium point where we want to provide some amount of goodness after some amount of the passes and allow that integration point to be durable and well-defined and one that's easy for libraries to use. And that's what we're representing here. So we will provide, we're proposing providing, having a well cleaned up, canonicalized, ideally suited for libraries integration point, both in the form of the HLO passes that you know and love today, where you can write your own pass to capture subgraphs and offload, or a being considered and developed MLIR style pass, where we can interchange between HLO and MLIR and allow you to integrate off that route to give you optionality in a world where more and more MLIR work is the standard. And then in the dotted line, we're showing that this kind of a number of things are culminating on this. We're making augmentations to our runtime, affectionately known as Thunk++, And we are thinking holistically in how we can have the work that's produced using the right ABIs go integrate with that scheduling piece so that we can provide good inter-op parallelism beside the intra-op parallelism we already get through libraries. So we're hoping to really address the library performance and then unlocking that to the maximum extent, and also providing the scheduling runtime capabilities in this holistic view. And again, this is a quick overview, then I'll dive into a little bit more of the bullet points here in a second. We chatted extensively with Intel, AMD, ARM, and a number of folks just to see, what would be an ideal situation for you and to find commonalities. We also talked to people like our partners over on the Erie team in regards to what if the microkernel approach that they've been developing, how would that dovetail with what we were proposing? And as I mentioned before, we found that the common request is to pave the way for this simple, predictable place where pattern matches can occur by having cleanup and canonicalization already happen in a predictable way at that point, and not having too much happen that has to be unwound, the proverbial turning hamburger back into the cow. We don't want to you have to rediscover things that are already expressed at a symbolic high level that have to be rediscovered if we lower too much. We also got some useful requests. Say you match a subgraph into a library offload, and then later on you want to deal with that subgraph in some other portion of your library or in your own sub runtime that you have. It's useful to retain that subgraph for later reference, to know what ops you fused into your custom call or offload. And we're going to provide a way to have those subgraphs be saved and referenced later in the pipeline. That actually feature was already in development, but it's just kind of seems like a universally useful thing to do. This and other topics are going to be and are being discussed now in the RFC, which I'm going to advertise now. It's no longer forthcoming. It was released yesterday. And please go to the forum and chime in. How about on the performance side? So today, one of the primary paths we do is we have kind of a combination of eigen and 1DNN working hand in hand for doing offload. And we already have a PR in progress to replace that with using 1DNN for the block, pad, and pack, and then 1DNN kernels using 1DNN for the whole end-to-end for at least that option path. We also got a number of requests for improved threading. We provide a pre-allocated thread pool, but we don't give you a mechanism to control the pinning, the affinity control on the threads. And this is something that just is universally needed, and we're going to address that, but it's still something that's being developed, and it's in the RFC also. Also, how big the pool that we create is a question mark. We make some naive assumptions on how many physical cores or logical cores you have and base the thread allocation based on that. That's not usually not often the right decision, and that's an area we're going to refine and improve. Another kind of idiosyncrasy of how the CPU compiler works today is that it's a monolithic compilation, and everything happens and is emitted into one translation step. And we believe that we know for certain that causes performance characterization problems in the sense that you just get one big function call in which all your profiling happens. We're going to break that into pieces. We also believe that's going to help with another problem we've had observations about, is that sometimes we have, shall we say, prodigious memory consumption during compilation. You should not have to be consuming the same amount of memory as you do during runtime just to compile the code. And so we believe that's a step that will help there. And I mentioned before interop scheduling. While that's not, at least in our predictions and what we've heard from others, although we'd love to hear from you, not like the super primary limiting factor in CPU performance, still there are gains that we've seen that could be realized if we had interop scheduling. And as the Thunk++ improved runtime system, which I'm not going to have time to go into today, but as that is being developed on the GPU side, we're doing that also for the CPU side in a common way. And then once we actually can break things into individual compilation steps instead of one massive file, we can then have something that can be scheduled at a granularity that gives parallelism. And that's in a nutshell, what we've got, again, I invite you to check out the RFC, and we have a breakout session at 4 to talk about this and many other things.
And I think we'll take some questions.
Please.
So I guess a bit of a naive question. I've heard that there's like a PJRT runtime for integrating with State Lake Joe. Hello, but here you're talking about Funk++. How are those two things related?
It's the interception point. So PGRT happens above, or instead of going down the XLA path.
I see.
Yeah.
Thanks.